All right, so we've come to the last video for Unit 3, which is uniform circular motion. So how do we kind of put all this stuff together we'll be talking about with um, centripetal force, centripetal acceleration, right? How does this apply with forces, and where we treat most of these uniform circular motion questions as Newton law questions, okay? So uniform circular motion, or UCM, are essentially Newton's second law problems that are hidden, right? So you have to figure out, what am I doing, right? And so you just follow those steps. So instead of objects traveling now in the horizontal and vertical directions, what I like to call it is the circular and non-circular direction. The circular direction typically will match up with the horizontal, and the non-circular will typically match up with the vertical, okay? Now, the non-circular direction is not accelerated. That's one thing to note. And the circular direction is what undergoes that centripetal acceleration. And then remember, we talked about this in the last video, the centripetal force is not a force that is drawn in a free body diagram. It is the net force in the circular direction, okay? So if I'm looking at my car, I wish this was my car, right? This is a Ferrari. You can see the little Ferrari logo right there, okay? So if I'm looking at my car, right, or this car, let me, if I'm drawing a free body diagram, right, I'm looking at this point right here. Now it looks like Rudolph, right? So now I've surfaced the surface, which means I have a normal force, okay? I have the weight balancing it. But again, this is the non-circular direction, okay? And then in the circular direction, I would have, if this car is rounding a curve, I would have friction, okay, into the circle. Let me get a different color. That kind of almost blends in with the background. Okay, so, all right, and so then we have this frictional force. So again, note, Fn and Fg are non-circular in this example, right? So note, in this example of a car rounding a turn, Fn and Fg are non-circular, and friction is the circular direction. Because there will be questions, or there will be problems, let's say, where these two actually sit in the circular direction. Okay, if I'm taking a loop in a roller coaster, those two, normal force and weight, would be in the circular direction. Okay, but on a car taking a turn, they're non-circular, which means those are the non-accelerated directions, and friction would be the accelerated direction. Okay, so let's look at a couple of examples. Okay, one of them will be involving cars taking turns, but the first thing we're going to look at is what happens if I go over like a hill, okay, or a dip in this case. So while traveling along a country lane with a constant speed of 18 meters per second, you encounter a dip in the road, right? So here's my car, right? I'm going to encounter a dip that has a radius, right, of 65 meters. And then they're asking, what is the normal force exerted by a car seat on an 81 kilogram passenger when the car is at the bottom of the dip? Okay. Again, circular UCM problems equals Newton's second law, right? And if you remember, Newton's second law are 3 steps: draw, sum, solve. Okay, so I'm looking at the person sitting in the car, but understand this: everything's doing this action. So the person's experiencing 18 meters per second in a dip that's 65 meters. Okay, so if I'm looking at the person on their seat, I only have 2 forces. I have the normal force that is provided by the car seat, and then I have the person's weight down. Now, if I have the dip, right, that means I have an inward centripetal force. So I'm going to draw it over here to the side. And generally, you're going to choose the positive direction to be, right, in the circular direction, right, or into the circle. That's right, into the circle equals positive, right? Whether it's at the top of the loop or the bottom of the loop or wherever, that's going to be the that into the circle will always be the positive direction. Okay, so there's our draw step. Now we're going to sum the directions, right? But the good thing is we don't have to worry about a non-circular direction because we don't have one. So we only have a circular direction. Okay, whereas if I do a T chart, I would do X and Y. Here I would do C and NC, right? So sum the forces, right? I have normal force into the circle minus weight, which is away from the circle, and my acceleration, right, is going to be my MAC, which is going to be into the circle. Okay. Now we know AC is equal to V squared over R. So what I'm going to do right now is I'm going to take that and plug it in there. Okay. Actually, let's do the algebra first. I'm looking for this. And so all I simply have to do is add that over. And so I get normal force equals MAC plus FG. But recall from Newton's second law, or from unit 2, FG equals mg. So I'm going to substitute that in here. And I'm going to substitute this. Now I'm going to take that v squared over r and put it there. And so I end up with Fn equals m times v squared over r plus g. Oh, sorry. I jumped the gun. I'm a little bit faster than I should. Right? So this is going to be mv squared over r plus mg. But it's the person. So what can I do? I can pull out an m, right? And I end up with mass times v squared over r plus g. Looks very similar to when we did apparent weight, when we ended up with like m times a plus g, or g plus a, g minus a. Very similar, right? Because guess what? Remember, this is a. So it has the same look to it. I'm going to move over here. So I'm going to say normal force equals my mass, it's my person, right? 81 times v squared over r. So 18 squared over 65 plus g, right? We'll call it 9.8. You can call it 9.81, 10, whatever you want to call it. We just know that the normal force experienced by the person is approximately 1,200 newtons. Okay? So that's when we're going like in a dip. It could be a roller coaster, right? If I'm looking at the top of the roller coaster. So one thing to note is that your normal force and your weight both point into the circle, right? So Fn and Fg point into the circle. So your equation is going to be a little bit different, but they're all going to be positive because remember, into the circle, right? Into the circle is our positive direction. Okay. Now, let's look at what happens with a tire, right? Or with cars. So you have a 1,000-kilogram car going around a curve with a radius of 30 meters. If the coefficient of friction between the car's tire and the road is 0.5, what is the maximum speed at which the car can make the turn? Okay. So start with our process, right? Draw, sum, solve. So draw a free body diagram. Fn, Fg, friction, right? No other forces acting. Those three forces, right? Normal force up because we have surface, weight down, which is always there with objects, and then friction, okay? The friction force, it doesn't matter where you put it. In fact, I mean, we can put it to where it's pointing. I'll do it in a different color. Into the circle, right? And again, it doesn't matter, but remember, FC pointing into the circle, right? Because remember, it's a center-seeking force, okay? So now is where I would do my circular direction and non-circular direction, right? So this would be equivalent of X and Y from unit 2, okay? So in the non-circular direction, I have two forces. I have normal force up, I have weight down, and that's going to equal to 0. Because remember, the non-circular direction is not accelerated. And so that just tells me that my normal force is going to equal my weight. Okay. Now, I'm going to leave that alone for right now because maybe I can do some manipulating of the equation, right? Do some algebra to get that mass to cancel out. Because guess what? Sometimes they don't give you that mass. Okay. It's good that they gave it to you here so you can plug in numbers to find and get an actual number for normal force. But let's go through and see if we can solve it without the normal force. Okay. Or without the mass. Okay. Now, in the circular direction, I have two things. I have one force. I have the friction, and that's going to go into the circle with the net force of Fc. Okay, but remember, friction is mu Fn, right? And so I'm going to say mu Fn equals MAC, but we found Fn to be Fg or Mg, excuse me. So I'm going to say mu Mg equals, and we also know that AC is V squared over R. So I'm going to plug that in. Okay. Same car going around the same turn. So here's the reason. Oh, sorry. Here's the reason why you don't necessarily need the mass, because look what happens when I solve. So I have mu G equals V squared over R. Well, that's kind of curious. Remember, we've been talking about this mu G kind of value. That's the acceleration of a sliding object. Right? So see, it comes back, right? We come back to stuff from unit 2 here in unit 3. We talked about this is the acceleration of a sliding object. Well, what does it have to equal? Yeah, of course it has to equal the centripetal acceleration because it's going around a turn. Okay, so now we get to a point where we can solve for V. So the first step, I'm going to multiply both sides by R. So I know V squared equals R mu G. And then my last step to get V by itself is to take the square root. Take the square root of V equals R mu G. And now I can plug in, right? So I'm going to say V equals the square root of the radius, 30, times mu, which is 0.5, times 9.8 or 10 or 9.81, whichever one you use. And you find that the maximum speed I can take this turn at is 12.1 meters per second. If I go anything greater than that, I'm going to go to the outside, right? So if you think about this, if I'm taking a turn, 12.1 is the maximum speed that I can go with. If I go greater than 12.1, I'm going to head off this way, right? And if I go less than 12.1, let me do that in black, I'm going to go this way, okay? Right, and so it's like I would skid out or I would skid in, right, or go into it if I went greater than or less than 12.1. Okay, so that ends the unit. See, I would say it was very short and quick, but you learned a lot from gravity to universal gravitation to centripetal acceleration to centripetal force, and then putting those two topics together into what we call uniform circular motion. Okay, look forward to unit 4 here in AP Physics.